Welcome to Natural Math, and today we'll be taking a look at another basic inequality. Let A, B, C be positive numbers such that A plus B plus C equals to 1. Prove that A minus BC over A plus BC plus B minus AC over B plus AC plus C minus AB over C plus AB is always smaller or equals to 3 over 2. Before moving on, don't forget to give a like to the video and subscribe to the channel. And now let's start. So the first thing to talk about is the Cauchy-Schwarz Inequality, which states that the summation of AI squared times the summation of BI squared is always larger or equals to the summation of AI BI squared, where A1 all the way up to AN and B1 all the way up to BN are real numbers, and they are not necessarily positive, unlike A and GM, which I covered about last video. And if you can't understand summations, this expression actually means A1 squared plus A2 squared plus all the way up to AN squared times B1 squared plus B2 squared all the way up to Bn squared is always larger or equals to A1 B1 plus A2 B2 plus all the way up to AN Bn squared. And in case you're wondering how we're supposed to prove this inequality, and now I will show you. So the first thing I want you to consider is this quadratic polynomial in ax squared plus 2bx plus c, where a does not equal to 0 or else will become a linear inequality. And we note that the discriminants, or here I'll denote as delta, is equals to 2b squared minus 4 times ac equals to 4 times b squared minus ac. But we know that if this polynomial, the roots of this polynomial are real and distinct, so two distinct real roots will give us a delta larger than 0, and two identical real roots will give us a delta equals to 0. And we know that if the roots are not real, so no real roots, will give us a delta smaller than 0. And how do we apply these facts into the Cauchy-Schwarz inequality to prove it? So if we think a1 b1 plus a2 b2 plus all the way up to a and b squared as 2b squared, so 2b, and this as a, and b1 squared plus b2 squared all the way up to b squared as c, and we will have a delta equals to 2b squared minus 4ac, and we want this to be smaller or equal to 0, so we have b squared smaller or equals to ac, which is our Cauchy-Schwarz inequality. So now we can construct inequality in a1 squared plus a2 squared plus all the way up to an squared x squared plus 2a1 b1 plus all the way up to an bn plus b1 squared plus all the way up to bn squared. And this will simply be equals to a1 squared x squared plus 2a1 b1 x plus b1 squared plus a2 squared x squared plus 2a2 b2 x plus b2 squared plus all the way up to an squared x squared plus 2an bn x plus bn squared. And this would be equals to a1x plus b1 squared plus a2x plus b2 squared plus anx plus bn squared. And this will be simply larger or equal to 0. And if this expression equals 0, it will give a graph that looks something like this. And it will look like a parabola which touches the x-axis only, and it will give us a delta equals to 0. And if this expression is larger than 0, it will give us a parabola which is above the x-axis, which means it doesn't touch the x-axis, so it does not have any real roots, which will give us a delta smaller than 0. And combining this, and we'll have delta smaller or equals to 0. And therefore, the discriminant of this entire polynomial equation is equals to 2 times a1 b1 plus all the way up to an bn squared minus 4 times a1 squared plus all the way up to an squared times b1 squared plus all the way up to bn squared will be equals to 4 times the summation of ai bi squared minus 4 times the summation of ai squared times the summation of bi squared. And since this is smaller or equal to 0, we can get the final inequality in the summation of ai squared times the summation of bi squared is always larger or equals to the summation of ai bi squared. And this will be known as the Cauchy-Schwarz inequality. And now, how do we apply this into our problem? So let's get back to the question and take a look. So first of all, when I see this very, very interesting expression, I want to convert it into something like this. So our expression will be converted to a plus bc minus 2bc over a plus bc, and we'll have 1 minus 2bc over a plus bc. And note that a plus b plus c equals to 1. So we have a will equals to 1 minus b minus c. And since 1 minus b minus c plus bc is equals to 1 minus b1 minus c, the original equation will be equivalent to 2bc over 1 minus b times 1 minus c plus 2ab over 1 minus a 1 minus b plus 2ac over 1 minus a 1 minus c, which is larger or equals to 3 over 2. And if we expand it, it will become 3 times 1 minus b, 1 minus times 1 minus a, times 1 minus c, large equals to 1. And this will become 4 times bc times 1 minus a, plus ab times 1 minus c, plus ac times 1 minus b. And moving this to the right hand side, we will have 4 times 3abc, 4 times negative 3abc plus bc plus ab plus ac larger or equals to 3 times negative abc plus ab plus bc plus ac minus a plus b plus c bracket plus 1. And we know that is equals to 1. So these two expressions actually cancels out. And moving everything to the left hand side, we will have negative 12abc plus 4 times ab plus ac plus bc plus 3abc minus 3 times ab plus bc plus ac larger or equal to 0, and we will have ab plus bc plus ac larger or equals to 9abc. Divide both sides by abc. We'll have 1 over a plus 1 over b plus 1 over c larger or equals to 9. And we now make use of our given condition a plus b plus over c and the fact that a, b, c are positive real numbers. So because that a plus b plus c equals to 1, a, b, c are positive real numbers. Therefore, a plus b plus c. Therefore, to make this clear, we have 1 over a plus 1 over b plus 1 over c is equals to a plus b plus c times 1 over a plus 1 over b plus 1 over c, which is larger or equals to, using the Cauchy-Schwarz inequality, the square of root a times root a 1 over root a plus root b times 1 over root b plus root c times 1 over root c. And it will be equals to 1 plus squared, of course, 1 plus 1 plus 1 squared, and it will be equals to 9. Therefore, successfully proved our what we wanted to prove. And to sum this up, we use the Cauchy-Schwarz inequality and some of the basic algebra techniques to transfer our inequality into what we want, and use the Cauchy inequality to prove it. I hope you enjoyed the video and learn the Cauchy-Schwarz inequality in GM and practice more, and you'll simply get better. And as always, until next time, see you in the next video.